So I would like to thank organizers for inviting me to this wonderful, I expect that should be conference dedicated to Sasha's anniversary. And it's a very great pleasure for me to participate in this conference, especially because we with Sasha had a rather long and very fruitful period of collaboration. What I will speak about today is a work in progress joined with Sergei Fernashin. And it's about counting lines and some other things. So let me start from definitions. So I think I should remind you, first of all, the definition of a del Pezzo surface. So X is a del Pezzo surface if its anti-canonical bundle is M. So as a result, it becomes a very nice family of surfaces. So in this case, so the k-square varies between 1 and 9. And if k-square is equal to 9, it is just projective plane. Then when k-square is equal to 3, this is a cubic surface. So non-singular cubic surface. So if k-square is equal to 2, then X is a double plane. Branched in a non-singular quartic curve. And finally, if k-square is equal to 1, it's a double quadratic cone. Double quadratic cone. Branched in a transversal intersection of Q with a cubic surface. In this case, which will be one of the main cases I will discuss today, I will denote by C this intersection. Okay. So I gave the definition of surfaces. Now I should define what is a line on the surface. So the definition is as follows. So A is a line if L is an embedded genus 1, genus 0. General curve with n square equal minus 1. So in other words, it's what is usually called minus 1 curve. Or exception, so on. But in the context of del Pezzo surfaces, it's natural to call these objects lines because, for example, in the case of cubic surfaces, they are true lines and they become true lines in P3. Okay, so what's next? So I gave the definitions. So important criterion. So L is a line if and only if just L square is equal KL equal minus 1.
And L is reducible.
Sorry?
And L is reducible.
No, for del Pezzo it's not necessary.
It could be a minus 1 divisor.
No, for del Pezzo it's not necessary.
Example.
No, in general it's wrong. In general it's wrong. You should, in general, you should add assumption irreducible, but in the case of del Pezzo surface, it's not necessary. So, and this is a big advantage. So it reduces the problem to arithmetics. Okay, so this explains why immediately why there are 240 lines on X when K square is equal to 1. So it's very easy. So then you just look due to this criteria. So you just look at the so that then in this case you have objection. Due to this criterion, you have objection between the set of lines and the set of root vectors in the orthogonal complement to the canonical class, which I consider as a part of, say, H2 of X with Z coefficients. This correspondence is straightforward due to this rule. Just when you have a root, you can build from this root a divisor which defines a line. So it's just minus K minus E. And after that, so you observe that the orthogonal complement to the canonical class is nothing but the famous root lattice E8. So you count the number of root vectors. And it's an easy exercise. It's equal to 240.
It's effective because the surface is not low, though.
Yes, yes, but this is a part of this definition.
Yeah,
So.
okay.
No, but thank you for the comment. It's really important, yeah. It's really important. So, but what I explained is something purely complex, purely classical, and our aim was, as easy to figure out, to find corresponding real results. What is happening with the reals? So let consider what is happening over the real field. So the next easy observation is the following, that if XR is connected maximal del Pezzo of degree k square equal 1, then all the lines are real. In fact, it's a part of a more general statement, also easy. But everything which I will succeed. Yeah, as usually. Usually of maximal complexity.
So what means maximal?
As usually, it means that the total Betti number of the real part is equal to the total Betti number of the complexification, which in this case, so we blow up 8 points. It should be 11 probably. Am I right? No, wait. 8 blow-ups of the projective plane, so it should give 11, yes. But it's not important for me.
This is total sum of Betti numbers.
Yeah. This is the definition of maximum. And more generally, for any XR, the number of real lines is equal to the number of root vectors in some lattice, and the lattice is just, as before, the orthogonal complement of the canonical class intersected with an eigenspace, eigenlattice of the surface. So I mean that it's the kernel of the 1 plus complex conjugation considered in, as before, in H2 of X. So I think I don't remember by heart the numbers. Probably I noticed it somewhere. Strange, I don't know. But Sergei certainly remembers the numbers. So in particular, so you may observe the following numbers: 240, 126, 60, 26, and 8. So
Nice comprehensible probabilities.
yeah. So I prefer not to enter in the discussion of this business, some lattice calculations.
But these are occurring numbers or all occurring numbers?
No, it's not all.
No.
I will precise. It's for simplest cases. Certainly, we know the answer, and it's easy to find for all the cases. But okay, already I spent too much time on this discussion.
If you add like 6, 4, and 2 and 0, then it will be all.
Okay. It's too long to explain. It's not so important. Just take a fun.
What in
Huh?
these numbers? What are these numbers?
This is the numbers of real lines. This is the number of real lines. But are you?
Of these numbers, there exists a surface with this number of
Stepa, wait a moment. Wait a moment. I can't answer to all the questions at the same moment. And in fact, I started a sentence and I didn't finish. So it's the number of real lines in the following cases. This is the M surface. This is only the series when xi is connected. So it's the series with connected xr. This is the maximal case. This is the m minus 1, m minus 2, m minus 3, and m minus 4. What it means? It means that in the first case, you blow up only real points. In this case, you blow up some 2 complex conjugate pairs, the other are reals, and so on. Okay?
In the beginning, that's simple. I mean, it's just
Yeah.
do all really blow down to.
No, it's wrong. This is just wrong, but these are the cases I presented at the table. I said that it's not all the cases. For example, as Sergey said already, if you take a disconnected M surface, then it just contains no line, no real line. Oh. Without any importance. Because what our goal is not to make a cardinal count of lines. We want to perform some side count of lines and to achieve the same body as in the case of cubic surfaces, where, let me remind you, that if you take real cubic surface, then on such a surface there is a notion of hyperbolic lines and elliptic lines. And if you count hyperbolic lines with the sign plus and the elliptic with the sign minus, then you get 3, whatever is the real structure. I mean that whatever is the cubic surface you have chosen. I repeat, our goal is to perform something, to find something similar in other cases. And so our strategy was the following. So probably many people in this audience know that this notion of hyperbolic elliptic can be expressed in different terms, but one of them is especially nice for applying arithmetics, is by means of pin minus structures. Sorry, I'm not going to give a definition of pin-minor structure, but let me tell that it's equivalent, choosing a pin-minus 1 structure on the real locus of a surface. It's equivalent to building a quadratic function defined on one-dimensional homology with Z2 coefficients, but with values in Z4. And probably many of the people in this audience know that in the case of cubic surfaces, there is a natural one, which appears just by taking a spin structure on the 3 space, and then observing that so then observing that it induces a pin-minus 1 structure on the real locus of the cubic surface. So we were searching similar construction in the case of k square equal to 1. And naturally came to the following construction. So if you take a anti-canonical map, on the del Pezzo of k square equal to 1, then you get an embedding of x not in this usual projective 3 space, but in a weighted projective space with weights 1, 1, 2, and 3. So this projective space is a bit singular. So here we have 2 singular points. One is 0, 0, 1, 0, and another is 0, 0, 1. Everything works over the real field, and even better. So over R, we observe the following, that only this one is this essential singularity. So Q is, how to say? Q is beta notation, P1, P2. Is topologically non-singular. Anyway, XR doesn't pass through these points. It is two-sided. And so the real locus, the smooth part of the topologically smooth part of the real locus of the projective space is just RP2 times R. So with this information in hand, you have a natural choice of a pin-minus structure.
So this projective is not compact?
Sorry? Compact.
I mean, this is compact on the left.
Singular part.
Outside the
Start to
P1.
put right somewhere, some symbol. Because you have written like projective space, like weighted projective space compact. It's just wrong. It's just wrong.
I said correctly, but wrote in a wrong way. So in natural choice, no, IP2, no, this is correct. P1, okay. So, sorry. I thought that this question is closed. So now the natural choice. So pick P minus structure on IP2 times R, which is essentially P minus structure on IP2. And then, using the fact that xi is two-sided, you get induced P minus structure on xr. So let me underline that in fact here you have two opposite P minus structures, and they induce also two opposite P minus structures on the real locus of the surface. And it's always better to make a unique choice. And here we have a possibility. So finally, we choose that one for which the value on the real part of the canonical class, which is the same thing as the first class of the real part. So we select that one which take one on this. And then we, okay, so now we have everything in hands, and we may start counting. So, as I promised, so the counting rule will be the following. So let's denote the number, I don't know why, in this way. Let me write the sum. This is the square root of -1. So you should diminish by 1 just not to work with imaginary numbers, but to have really a signed count. And we, naturally what we did, we took such a sum over all real lines. And on our del Pezzo surface. So we made a count. So as a result, we have obtained the following numbers: 16, 14, 12, 10, and 8. So as Step asked me already once, this is for which kind of surfaces? Always the same. So I could continue, but I think that this step is enough. So it's for the cases when the real locus is connected.
These are the values of NN,
Yes. Yes. So again, m minus 1, m minus 2, m minus 3, m minus 4. So, what it means? We failed. No invariance. So, where we are wrong? This is a question to the audience. What is wrong?
I think if they were an invariant, it would be 0.
Sorry?
If they were an invariant, it would be 0, because as Sergei said, there is a case when the total count is 0.
Wrong answer. Other suggestions? Fabrizio.
I'm trying to understand. I mean, why I is the square root of -1?
Because the self-intersection number is -1. So it's not two-sided, the real locus. So on such kind of cycles, Q takes odd values. So if you want to work with signs, you're obliged to do that. Okay? So, but the answer is the following. So, I'm really surprised that nobody answered the question. I hope that it will not be the case. But if honestly, it took for us to understand some time. It took some time for us to understand. Sorry?
It's a joke. See, where we are wrong,
Yes.
and
Okay. So, what we in fact what we are looking for.
there's some orientation of what is the meaning of this sign?
It's a different story. Let's postpone it to the questions. If not, I will not succeed to tell much. Already I'm drastically late. So the story is the following. So we are working with H2 of the of our surface. But we are interested, in fact, in counting only effective devices. And the effective devices, they form a cone in H2. So you have this cone in H2, the cone of effective cycles. It's true that main building blocks of this cone are the lines. So you have the lines, which are generators of this cone. And this cone can be sliced by levels, by taking exactly as I wrote somewhere, so minus kd. Minus kd is equal to 1 if d is equal to L, is a line. So we are on the first level. So as I said already, but didn't write, so the lines generate this cone over Q, but not over Z, Q plus, but not over Z plus. So there is one more vector which you need to add to the lines to generate the semi-group of effective dividers. And this additional generator is our d equal to minus k. So the correct counting rule is the following. Okay, so it's like before, the sum of the lines I Q L R minus 1, but you should also count real rational curves A in this additional divisor class. Do the same. But this time, since the curves are no more non-singular, you should take into account the nodes. And so as Viatcheslav learned us, we should put here something. So we were obliged to change a little bit his signs, and so we count, instead of solitary points, we count the number of cross points. But nevertheless, I will denote this as W will changer number of A. Okay? And this is also easy to count because, in fact, in this case, these are just curves of arithmetic genus 1. So you may use an elliptic pencil to count everything by means of the Euler characteristic, and then to use Lefschetz trace formula, blah, blah, blah. No problem. And the answer is that the correct number is equal what usually appears in real algebraic geometry, in topology of real algebraic curves. Which number? No, it's number. It's a constant, it's invariant. Which is the most current number in topology of real algebraic curves? 16. No, I don't agree with you. It's 8. But it's almost 16, yeah. Okay. So, I have already explained the proof. So now, since I mentioned elliptic pencils, Euler characteristic, Lefschetz trace formula, so nothing else. Very simple. But after these observations, we could go much further. If honestly, not very far, but much further. So now, so So why count only lines? Why count only curves on the first level when there is infinity number of levels? So let's try count on all the levels. So general counting of real rational curves on del Pezzo surfaces with k square equals 3, 2, and 1. This is what we know to do for sure. So, the main certainly is to fix counting rule. So let me write first the formula, and then I will try to explain what it means. So it will be sum over some real rational curves A belonging to some level and here it's a square root of -1 q r minus m square w a r. So now I should explain. But in fact, so what is Lm? I have already explained. So Lm is just all classes in H2 minus is given intersection with the anti-canonical class. And n. Sorry? Sorry?
Square is fixed,
No, just a level, just a slice of. And I add some other homology classes, but anyway, there will be no curves to count there, so I don't mention it. But I have forgotten. So I should explain this k, and then I should put it here. So real rational curves such that A pass through given points. So real set of M it's M minus 1 points K K of them are real, taken real, and suddenly everything is taken with general position. Okay, no mistake. I can go further. So to explain what is Q, it's Q corresponds to a p-1 structure induced by a anti-canonical embedding. So we have the case of projective space. The case of the weighted projective space. And the case of another weighted projective space correspondingly to the case of k square equals 3, k square equal 2, k square equal 1.
You mean big K?
Sorry?
You mean big K because now you have K which looks very similar.
I don't follow.
Now you have K
Oh,
which looks very similar.
I will not correct.
I got confused.
Yeah,
Now it's
I'm sorry, but I will not correct.
Not k square by b.
No, I don't want correct. I don't want correct. So, small remark. So, there is a unique choice when k square is odd, and two opposite choices. We are not able to select a unique one. Two opposite choices when k square is equal to 2. And furthermore, starting from here, even if I have very few time, but nevertheless, not to repeat it each time, starting from here, I always will assume that the real part of x is non-empty if k square is equal to 2. Okay. So now the theorem, the main theorem is that with such a choice, yes, and k doesn't depend on the real structure. Certainly, it's up to sign if k square is equal to 2. So I should select what to say in the remaining 10 minutes, what I think more important to say. So first of all, so I think it's remarkable what are the remarkable things to cite? There are simple, explicit recursion formulas for these numbers. I will not write these formulas, but you can, if you are interested in, you will find it in our papers. They are already published. Yes, I see. No, this is on archive. And moreover, as a consequence of these recursion formulas, you can get even explicit formulas for these numbers themselves. This formula, let me give you. So the story starts certainly from some vanishing result, which is essentially to Brigalet. So these numbers are 0 as soon as m is not congruent to k modulo 2. This is evident. K plus 1, sorry. K plus 1 modulo 2. What is less evident is that, and here you should ask Brigalet, if k is greater or equal to 2. They're just zeros. But the other ones are not zeros, and they behave as follows. So the final result, the explicit formulas are nm0 equal 1 over 4 n 1 0 b power n plus 1 over 2 power n minus 2 if n is equal to 2k plus 1 and n m1 is equal to n to 1 b power n minus 1 n power n minus 3. And in both cases, b is 4 times n to 1 over k squared. Sorry? N should be m. Thank you, Sasha.
In the second case, the m. Okay, m.
Okay, so I have how much? 7 minutes. But no, anyway, I think it's not reasonable to start to bifurcate to a bit another situation. Let me just give you some opinion. So what is, by my opinion, what is important in all this story? So first of all, what our Q has so special? Apparently, if I'm not wrong, the only really the main thing which we use in proofs are the following two properties. First, Q vanishes on every vanishing cycle, on every real vanishing cycle. And B the result so the final result. Oh, sorry. It's other remark. So, sorry, I'm thinking. So the second one is that Q is deformation is invariant on the real deformations and real isomorphisms for given class of surfaces. So this is the first point. And then what is so important in the choice of del Pezzo surfaces? Your opinion? No opinion?
As opposed to what?
Sorry?
As opposed to what?
For results to be true.
No, but I mean del Pezzo as opposed to what? The general type or to other rational surfaces?
Oh, to other rational surfaces, certainly. No. Well, okay, so we are simple people. We are not inventing objects. We just count them. So, yeah. So your answer is not quite right, because it's more about the proofs than the question. Because the appearance of nodes, they abstract the invariance. But we nevertheless want to have an invariance. So we should avoid this abstraction. And by my opinion, it's doable in general. But what helped us imagine, it was crucial in my presentation from the very beginning, from the very definition of del Pezzo surfaces, that minus k example. Semi-ample, it's not an abstraction. What is really important is that minus k example, because otherwise what I'm speaking about. So I wrote some sums, nobody asked me, and why this sum is finite. And this is exactly what is changing when you pass from blowing 8 points to 9 points. So the number, already the number of real lines becomes infinite. So how to write a sum? What is the answer?
Integral.
You will explain me. I thought about that, but I didn't succeed to find a nice integral. But there is another simple solution. It's another simple idea.
Well, I think wasn't it just my question in the beginning that since minus k is ample, a -1 divisor is irreducible, and so you get lines and not complicated divisors.
Yeah.
This is one feature. Maybe it's not all, but
Yeah. But there is another simple idea, which I hope I will be able to present the next time, is just to change your divisor. If minus k is not ample, just add something to it to make it ample and start to calculate. And I believe that with a good choice, which we have in mind, this not only will be finite, but will give such a strong surgery invariance of counting. I think I should stop here.
Thank you very much.